Hello, welcome to another segment of the virtual summer camp from the USC College of Engineering Computing. This is basically the fifth segment talking about circuits, electricity, and microcontrollers, computers, and a little bit of aerospace. Basically, we're going to talk about Arduinos. It's not going to be as much a lecture about theory and talking about that, but talking about this little computer. It's really a cheap little computer. It does basic stuff. You can program it like a computer, but it doesn't have a lot of power. It's an interface to the real world. So it's not inside a computer. It basically sits on its own. It has inputs and outputs. So it can read data, like there's a button pushed, and it can blink lights or turn on motors in some cases. So the computer is super, super simple. 32 kilobytes, which is only 32 kilobytes is not even a megabyte. It's a tiny, tiny amount of memory. So that 256,000 bits, 8 bits in a byte. So it's not a lot of memory on these devices. Some of the Arduinos are a little bigger, but they're basically very simple little computers. But there's a large community out there. And you can look into Arduino projects. And when you're starting out with anything, it's great just to do a tutorial. That's why we do tutorials. You follow the tutorial, you do it, you learn by doing. So find somebody's project that doesn't look too complicated and you copy it. And even just copying their project, you'll run into issues and learn how to problem solve and fix. It's not easy just to copy somebody's project typically. You have to figure out, it's not exactly matching, so you have to figure out this, that, or the other. So copying a project is a great way to go. Running through tutorials, it helps you form a foundation for later on. You don't go straight into the circuit design. You go start off, let's just make a light blink. And these Arduinos have gotten pretty inexpensive. The little one here is a Nano. It's maybe $10, $12 for maybe a Arduino compatible. Arduino is actually an Italian company, but they've been pretty open about their specifications. So there are other companies that make Arduino compatible hardware. The Uno is this other one that's a little bit bigger. It has a little bit more power, a little more inputs and outputs. So either one, they're very similar. Basically have similar interface, very compatible for projects in many cases. There's another one I'd like to talk about eventually is microbit. There are two different things. The microbit's sort of similar. It's not very expensive. You can program it to do things. You put a little computer program on this little computer. It's the same kind of idea, but it comes with 2 buttons already wired together and 25 LEDs. So it's like a little mini display. You can hook it in and use some of these pieces of metal on the bottom. So you could hook it into circuits and use it like that. But out of the box, it comes already wired together. So you don't have to fuss with getting wires and buttons and LEDs wired together to make it do something. So it's a little bit simpler if you don't want to play with all the wires. The wires and buttons and things, you can still add, but hook it into using these connections, 0, 1, 2, 3, and interface with other things. But out of the box, you can start playing around, and it's easy to get code onto this thing and make it run. The Arduino is a little more difficult to do in the real world. So today I'll talk about the Arduino, and then I'll show you how to set up a simulation of the Arduino, and then show you how to do the real world Arduino if you want to put together a little kit that matches the simulation. So you can just, if you don't have the hardware, you can just do the software. The software is free. There are some example projects out there. Somebody made a art project where you have these little feathers on motors and they move slowly. So it's a little creepy, but the computer, it's basically a computer. All it does is rotate the feather on a motor. Fellow made a railroad in his backyard and controlled everything. It's just simple button presses. When I do this, do that. So simple logic can be implemented in the computer to make things happen, like motors run or lights turn on when you push buttons or when you have a sensor or a safety sensor in some cases. Somebody made a door chime. So that's basically hooking in with a personal network in their house so they have a door chime. So the Arduino output pins, so these little pins are electrical connections. Those wires can send stuff out into the world, so a signal. It's usually a 5-volt signal. not many milliamps. So voltage is like pressure. We'll talk about this, but basically it's not a lot of power, but it's enough. It's a little bit of information. And we treat this as low or high, close to 0 or close to 5. So it probably won't run a big motor for a scooter, but it can turn on a little LED light. There are also input pins that can read signals from the real world. And those signals can be two different types. A digital signal is either low or high. So it's either, is it below like 2.5 volts? That means it's low. It's above 2.5 volts, it's high. So there's a cutoff between there. And they're analog, digital and analog. Digital is discrete, analog is sort of continuous, but in this case, it only reads values between 0 and 5 volts split up into 256 different values. So it's not very high resolution. It splits up all the voltages between 0 and 5 volts, and 0 is 0 volts and 5 volts is 255. So anything above 5 volts would be 255, and anything in between there is split up into 0 to 255. You plug it into a computer and you get power from the USB, or if there's a power adapter, you can just plug it in. If you program it and you're happy with the program, you plug it into just a USB power to run electricity into it. Looking at the Arduino, it has all these different pins. For this project, we're just going to use 2 output pins and 2 input pins. In this case, for the Nano, there's a ground pin and there's a signal pin, and there's 2 of these digital pins, 12 and 13. But there's other things. You can do all sorts of things on there. And there's even LEDs on the board that show that if it's getting power and if you're actually making it do something. Breadboards are an interesting thing for electrical engineers, for people taking circuits. It's a quick way to hook up wires so that you don't have to do soldering or use electrical tape to put things together. So if you want to make a prototype or test a circuit, you can put it into a breadboard. If you turn over some breadboards, you can see on the back, everything, all these pins here are connected. So all these rows are connected. So if you stick a pin, there's 1, 2, 3, 4, 5 different holes there. So all 5 of those holes would be connected. It's like putting 5 wires together potentially. But on a bigger breadboard, which you usually see, you have the 5 rows, 1, 2, 3, 4, 5 rows, and a channel, and then 5 rows. So a lot of your chips will fit across this channel. So you have the left side and the right side. And then you have these vertical columns. One is red, one is blue. One is red, one is blue. Typically, you have to have a ground and a supply source, so like high voltage and a ground. We'll talk a little bit more about that, but all of these vertically are connected on this side, and all these vertically are connected on this side. Jumper wires help you hook things together. So if you have a lot of male-to-male, you just stick them right into the breadboard and you make connections pretty easily. And I like these jumper wires compared to regular wires because they have a hard metal stiff post that goes right into the breadboard very easily. You just jam it in the hole. When I was a kid, I had some kits and I had to play with wires, and it's hard to get wires, just a regular wire, they bend a lot. So having a nice jumper wire with a pokey end is very useful. You typically use resistors. A resistor resists the flow of current. It's like a valve. If you think about water in a pipe, a resistor is like a valve that basically holds up the flow of current. And if you put too much current through some items, they break. So some of the lights, the light emitting diodes, LEDs, they will burn out if you put straight current through them. So you have to put a resistor in there to slow down the current so not so much current will flow through it. And that's really how a fuse works in your car or your house. Well, these days you don't do that in your house. They used to have fuses in your house that would burn out. But in a car still, they have fuses. If too much current goes through a circuit in your car, it will burn out a fuse, and that fuse is broken and you have to replace it to get that circuit to work again. And that happens if you have a short circuit. The LEDs, we're going to light up LEDs. They're super efficient. But one of the interesting things about an LED, it's a diode, which means power only flows in one direction. So current's only flowing one way. The short end is closer to the ground. So it goes in the big end and it comes out the short end. And this is frustrating to me. I always forget which way it goes because I'm just forget. and I have to flip my LEDs backwards. When I'm doing this in hardware, I always forget which way to go to test it out. We'll have some buttons. Buttons allow contact to be made, so you can mash the button and then you can connect and disconnect a wire basically. And most of these are crisscross buttons. They have 4 connectors and they crisscross with 2 separate lines typically. The Arduino input pins are a little weird in how they work. We'll discuss that more when we're talking about the simulation. So you push the button to connect the input to ground to read a difference. So the input pin has a voltage, so it's sitting there at 5 volts, and when you push the pin, it connects it to the ground, and that voltage goes down. So you can detect the difference between high voltage on that pin and low voltage on that pin when the button's pushed. So an electrical engineer might come up with a circuit diagram like this. You got your Arduino, or whatever chip. In this case, the Arduino Nano looks like a chip. And you hook up different pins, and you have, this is a symbol for LEDs. You have a symbol for resistors, the 220 ohm resistors. You have a switch. So this would be the diagram for a design. And then you actually have to build it from that. Like I said, breadboards are connected. So all of these are connected up and down across the middle section, and the red and blue lines are connected, in this case, horizontally along these arrows. So that saves you time for hooking together. The actual circuit I showed you before in real life looks more like this. You get your Arduino, we have 4 connections to it. We have resistors and LEDs and wires. We have the ground down here on the bottom. There's a blue row all connected. That's the ground voltage. So all of those are connections through a resistor. I'll talk about them in a little more detail. So let's see, the output pin, the input pin for the button, output pin for the green LED, output pin for the red LED, LED and the resistor, LED and resistor, little jumper wires here, the USB connection. But here's a stylized, cleaner version, again in some simulation software. So you can put the Nano onto the board and the button, and the resistor, and the LED. And when you wire it up like this, it should actually work if you have good connections. But again, doing the hardware is sometimes frustrating because you don't have it in the right pin. You have to look very carefully. Are they in the same row, or did you miss a row? It's a little tricky when you're first doing it. So we try and start out with something simple. So in this case, for lighting up the red LED, if you tell the Arduino to turn on this 1 pin, so that means electricity is flowing at 5 volts from there. It goes from this corner, from that pin, through the wire, into the breadboard. It goes down to the breadboard, connection and that through here, to the long leg of the LED. Electricity goes down the short leg of the LED through this resistor. So all of these 2 pins are connected. It goes through that resistor, through this connection, through a little black wire to this column. This is the ground, and the ground, the electricity goes back into the ground. So you've made a whole circuit. You have to have a circuit for electricity. And again, I don't think I've talked too much about the analogy that made sense to me. Circuits didn't make sense to me. I played with circuits as a kid. I could follow tutorials and build stuff, but it didn't make sense. I took physics in high school and physics in college and circuits class at Georgia Tech in undergraduate, and it still didn't make sense. Eventually, somebody made an analogy. A battery or a power source is like a pump, pumping water. And that water has a pressure and a flow rate. So if that water is going to go out and do some work, in this case it's making electricity or going through a resistor, that's like water going out from a pump and doing something like turning on a light or running a turbine to spin something, and then it has to make a circuit, so it has to come back to the pump. So you're pumping the water out to do some work, and then it comes back to the pump. And that's an analogy that made sense to me. It starts at high pressure, that's like voltage, and it's how much work the electrons want to do, it's how much the water wants to work. And then the current is the other one, how much electricity is flowing, how much water is flowing in that pipe. Is it a small pipe? Is it a garden hose? Is it a fire hose? Is it a river? So that current and voltage are two different things. Current and voltage sort of correlate to pressure and flow rate for water. So if you think of it as a liquid circuit, for some people, it helps me a lot understand about making a circuit. The other LED has a different pin. So when you turn that pin on, when the computer turns that pin on, electricity is going to flow into this row, actually column, through the long leg of the LED, down the short leg, through this part of the breadboard, through the resistor, to this connection, back to the ground, and ground. All of these ground, since they're at 0 volts, all of them can be connected together. So usually that's why you call it ground. It's a ground state, 0 voltage, but it still needs to flow back into the equipment, into the computer. The button's a little tricky. He's connected crisscross, and he sits across this channel, and we're going to connect him to ground. When you push the button, it connects this pin to the ground, so it goes from 5 volts to 0 volts, and that's what you're reading. And you can read that as an input to the computer and input to the Arduino. So really, one of the interesting things to think about, these are the 3 different views. So the real world view has wires that aren't straight. The idealized view has beautiful wires, everything's organized, and then the actual view from a design perspective, once you get to know these really well, you can start thinking in terms of these kinds of wiring diagrams with symbols. So to start this project, I'm going to talk you through it the first time. I'll post this as a PDF so you can go through it in your own time, but this will show you what you're up against. You log into TinkerCAD, make a new project, maybe you may have to make a new account. You start off, and there are parts over here, and there's an area where you can build stuff. So you're going to drag into the left a breadboard and some batteries. We're going to hook the power source together. So this breadboard, we're going to play around with LEDs at first. So the breadboard has these batteries. We don't have wires yet. So you can click on different connections to wire together, just like you have a stack of batteries, you put them in series, red to black, and then you have red, hook it into this red channel, and you have the black, the ground, and hook it into the black channel. So that the top and the bottom are connected, carefully hook this guy from the top red to the bottom red, and the other guy from the top black to the bottom black. So that way, the top and the bottom both have plus 4.5 volts. We have 3 batteries in series, so you're stacking 3 batteries together. 1.5 volts plus 1.5 plus 1.5 is almost 5 volts. So it's pretty close to 5 volts, 4.5 volts. And then you have basically powered up your breadboard and you have your ground circuit there. But nothing's flowing, nothing's hooked up. It's probably good practice to click on those wires. You can change the color. So the red ones that are hot, you can change them to red, and the black ones that are grounds, you change them to black. Sometimes it just simplifies what you're looking at on a breadboard if you can use color-coded wires. It doesn't matter what color the wires are, but just sometimes the color coding can help you. So you can drag in an LED, and remember the power goes in the long leg. You can drag in a resistor. In this case, I stuck the resistor across the channel on the breadboard. So when you plug that in, electric current's going to come from the battery. You add this wire here, so it's going to hook in from 5 volts into this part of the LED. Through the LED, these are connected because that channel, all of these guys are connected. So that back end of the LED and the resistor are connected. Through the resistor to the ground, and that ground goes back through this bottom ground wire across to this ground wire and back into the battery. So that whole cycle there, the electricity is going through that cycle. High voltage, through the LED, through the resistor, through the breadboard, through the ground, back into the battery. If you run the simulation, there's a simulation button, start and stop the simulation, the light should turn on. So you stop that simulation. Another thing, change the resistance to 220 ohms, not kilo ohms or milliohms or mega ohms, 220 ohms, so you can change that. And you can see that the resistor changes the bands on that. So that's how you can look at the resistor and tell, depending on the colors, what resist resistance it is just by looking at it. But sometimes they're tricky to read because they're tiny. It's hard to see the colors exactly. But there's a color coding for all of your resistors. You can do the same thing to add another 220 ohm resistor and a green LED. Put them together and hook them both together. So when you run the simulation, both the LEDs should light up. So you basically made a really bad flashlight. Nothing too exciting. If you put a button in there and change the wiring around, so you delete the wire for the red LED, now this button is a little bit interesting. He's hooked into plus 4.5 volts down here on the bottom red line. So electricity will be trying to flow through here, and it won't flow until you push the button. When you push the button, electricity will flow across that button into this channel, across this wire, and into the LED, through the LED, through the resistor, and back to the ground. So it's basically a flashlight with a switch. So simple circuits showing you how you can use LEDs and how you can use buttons. You can have to run the simulation every time that you want to see it working. So every time you push that button, the red light should turn on because it's getting current. When you release the button, it's not getting current. So if you delete those batteries, pull in an Arduino. The Arduino has a special hook for 5 volts and ground, so you can just hook those in down here. So now it's the same circuit as before. It should work. When you run the simulation, the green light should always be on because it's getting power, and the red light will only be on when you click on the button to turn it on and off. The Arduino, though, has code, so you can click on the code button and it will open up code and let you see that. But before you do that, let's change the red LED. So this red LED, instead of hooked into the wire, delete its wire and hook it into this pin 13 over here. So you're going to hook that wire to that red LED so that when the Arduino brain turns on pin 13, that will send power to the red LED, 5 volts of power. So looking at the code for this guy, the code for this guy looks a lot like Scratch code. So by default, it has this blink program. It's going to keep running this over and over. It's in a loop. So it sets the built-in LED to high. It waits 1 second and then sets the built-in LED to low. So it's going to oscillate between on and off, on and off. So that pin 13 is going to turn on and off for 1 second, back and forth. When you run the simulation, that's what you should see. So when you run that simulation, it should blink the red LED because it's hooked to pin 13, and that's the built-in LED. You might also see a little LED blinking as well because it has a LED there to on the board that blinks, and that's how I know. I like to run the blink program to make sure that it's doing something. And sometimes I'll change the interval to like 2 seconds so I know that I'm actually changing the code and it's actually getting the new program just to debug and figure out what's going on. But after you get that red LED blinking, you know it's alive and it's working. You can hook up the green LED to a different pin. So we put him on pin 12. So pin 13 and pin 12 are hooked in. One's for red, one's for green, and the button's not hooked in yet. But we have to change the code. So now you can get different code. Over here in the code, you want this high-low set. This one down here is for analog. So there's analog in and analog out. You don't want to use him, where you can actually change the number. You want to just be able to use the high and low values. So you set pin 13 and 12. In this case, I set pin 13 to high and pin 12 to low. So turn them off. Wait 1 second, then I swap it. 13 goes to low and 12 goes to high. So it should blink back and forth. Red, green, red's on, green's off. Red's off, green's on. So when you run that simulation, it should work. Now let's get the button working. In this case, you have the button there. We want to connect this guy. He was connected down here to the red, to the hot, but now you want to put him into the ground. So you move that wire to the black ground. You've got this button. He's connected to this column of buttons here. So you hook him into pin 0. We're going to read pin 0 as an input. And I also put a voltmeter in there so that when you run the simulation, you have the black connected to black and the red connected there. when you run the simulation, it's going to look like this. If you're not pushing the button, it's going to be at 5 volts because this pin sits at 5 volts. When you push the button, it's going to drain some electricity or power off of that pin to ground, and the voltage on this point is going to go to 0. So you can check that connection. And in reality, when you're doing some of these hardware things, you have a voltmeter, so you can measure voltages on your breadboard. So you can look for, is this getting power? Is this getting power like I expect it to? Is this the voltage I expect it to be? So this is nice in simulation. You can hook it in and investigate very quickly what parts of your simulation are getting power. So to make that button work, again, this is your code. It's going to check that digital pin 0. When it is set to 1, it's going to do this. Turn on pin 13 to high and 12 to low. And every time, otherwise, it's going to be doing this. Setting 13 to low and 12 to high. So that's a simple project to basically, when you push a button, toggle it to the other state. You go from low and high to high and low. Actually, this is the button push and this is the not button push. So it's just showing you can make things work. You can make your own program that changes the behavior. Now, one of the interesting things about this TinkerCAD software, actually, this is an example. When you push the button, this guy goes to, when you push this button, it makes the voltage go to 0 on that pin. So it switches to the other state. So that's this is the button push state. This is the not button push state. When you go into the code menu, you can download code. And if you have the Arduino software installed on your computer, on a PC or a Mac, you can open that file, and the actual file that you would have is what we usually see for Arduino code. It's a lot of text. So that text code has all this information about setting up the problem and doing stuff, an if statement and commands, and these are comments. So that's what you traditionally work with in Arduino. But this TinkerCAD is nice because you don't have to worry about messing up the hardware or breaking hardware or broken hardware or forgetting a semicolon. So, but you can, once you test it out in TinkerCAD, you can get a file that you can run on your Arduino if you have a hardware, an actual real life Arduino. So one of the things to notice about this code, that we haven't seen real code yet. We played with Scratch a little bit and we saw that code for the Arduino. Everything in gray in this editor, everything between this character is documentation, doesn't mean anything. It's just text. Everything on the same line as a double hash or a double slash is ignored. So all the other stuff is important. You don't have to have comments, but it helps you understand. Each comment or each command usually ends with a semicolon. Functions put input arguments in parentheses, and chunks of code have matching curly braces. And you try and use indentation as well. So all these functions, you write to a pin a high value, you wait 1,000 milliseconds. You write to a pin a low value, you wait 1,000 milliseconds. So that's the basic code. To get an Arduino running, you have to log into the computer, plug it in the USB, get it connected, get the drivers installed. Sometimes it's a headache to get the Arduino drivers working. When you have to start the Arduino program that does the programming that communicates with the Arduino, you have to figure out which serial port it thinks it's using. And this is one of the worst parts about using the Arduino. It has used these old COM serial ports that are 30 or 40 years old, and they still work on a PC, sort of. You typically have to tell it what board you're using. It could be an Arduino Nano, it could be an Arduino Uno, it could be different chips. So sometimes they auto detect, but there's a lot of different Arduinos out there, and you have to figure out which one you are using or which one you have, and hopefully it's on the list, and hopefully it works, and hopefully you get the right COM address. I like to select from the example files the analog blank, and it opens up a text file. And it shows you the blink, the simplest program pretty much. Then if everything's hooked up, I like to hit this right arrow. It will convert this text, all this program, into the code that the Arduino understands. It may take 10 or 20 seconds. The Arduino might flash if everything's working. And then if it is working, your Arduino should go into this blink program, which basically turns on the onboard LED for 1 second and off. The Nano has it onboard, and the Uno, and I think all of them have that. Pin 13 is the built-in. So this program should tell you if it's working. And like I said, I like to change the delay here, maybe change 1 to 2000 so it'll stay on or off for 2000 seconds and rerun it just to make sure that I'm actually I'm making a change in the program, and it's when I compile it and run it and download it to the Arduino that it actually is getting onto the Arduino. So you can change the program. You can understand what these different things are. This is an example changing it to 100 milliseconds. So it's going to be on for 1/10 of a second and off for a whole second. So that's testing the program to make sure it works. Here's program B, where we have, instead of using the built-in, we have variables now. Red LED, green LED. We put those into different pins, or you can put a number there. So if you change your pin to a different location, maybe you want to use 10 and 11, you can just change it there, so you don't have to change it throughout your program. You have one variable that if you want to rewire your hardware, you can just change it there, and everywhere else in your program, it will know, okay, instead of going to find every place where I use 13, I'm using red LED or green LED, so I can change it in one spot and my whole program would change. You have to set up both of those pins as outputs. Sometimes the Arduino can be input or output, and then you have to write your program to turn them on and off. You can have an input pin to find what value that is. And this is a simple program that's going to loop through. It's going to write something to the pins, and it's going to wait 1/10 of a second and then check that input pin. It'll do something if that pin is low. So it's basically cycling through, it's doing something. This is a more complicated program, so it's going to read and change variables and do some more interesting things. But basically, you can make fairly complex computer programs and behavior just by understanding the inputs and outputs. The Arduino reads from the button presses and it sends signals to the LEDs. So this program, if the pin is high, it's going to put red off and green off. So if the pin turns on, it's going to have the red light for a second, and then it's going to turn it off, and then the green light for a second. It's sort of like a starting gate. So when you're starting your Pinewood Derby car, possibly, something like that. What does this all relate to? Electrical engineering. Electrical engineers are the guys that focus on everything that uses electricity. Circuit boards, computers, power, distributing power, generating power, using power, making motors, designing motors, semiconductors for computers that are on-off switches with electricity, semiconductors, even photovoltaics, generating electricity from the sun. So electrical engineering does stuff with electricity. Another area we haven't talked about yet is aerospace engineering, which is basically the design of devices related to aircraft and spacecraft. So aerospace engineering, they work with airplanes, rockets, drones, engines, specifically for aerospace. A lot of what they do relates to mechanical engineering, but a lot of it overlaps with electrical engineering in some cases because of control systems. And actually, we have a lot of chemical engineers that have gone to work for Boeing. A lot of their stuff is working with lightweight strength composites. So aerospace does a lot of different things, but they're sort of stuck in the aircraft, spacecraft industry. So one of the projects to look at is a little involved game looking at the Wright Brothers, going through and helping them design the first Wright flyer. So it's a nicely done from the Smithsonian Institution activity. But one of the things to remember, weight and lift are two forces. The weight of the plane pulls it down, the lift from the wings pulls it up. You don't think about drag, but drag is when you're flying through the air, you have wind resistance, and that amount of drag pulls you back. You have thrust, your engine, your jet engine, your propeller is pushing you forward with a certain force. And if all of those forces are balanced, you're going to, if the lift and weight are balanced, you're not going to go up or down. If your drag and thrust are balanced, the same amount of force, you're not going to speed up or slow down. So you're going to continue on at level flight without speeding up or sinking or accelerating, slowing down, speeding up, or going down. Now, usually for summer camps, we've done an airplane challenge. So your goal is to make an airplane for maximum distance per dollar. So there's economics that goes into this. And most of engineering, we don't stress this enough, that you need to worry about economics. So your plane requirements, you have design requirements. Your plane has to fly at least 10 feet. You have to purchase a design. You can't just wing it with a design. You have to pay for design, and you have to buy materials, and you have to pay for every test flight. So your goal would be to maximize the ratio of distance per cost. So if you go $10, 10 feet, you've met the requirements, but your plane may cost $100. If you go 20 feet and your plane costs $100, you've obviously done better. So that ratio, you have to get a factor between distance and cost. So typically, I show the designs. You got 4 different designs. They cost different amounts. Simple design, dart, buzz, hunting. So you have to determine which one you want to invest your money into. Spend more money for one of these, like the dart, or less money for some of the other ones. See which one, you have to think about the trade-offs. Which one is going to give you more distance, and which one can meet the requirement of 10 feet. So usually I charge for basic paper or thicker cardstock paper. Cardstock is more, construction paper is more. If you want to add Post-it notes or paper clips, you can buy those. But every test flight, every time you throw it and measure it, costs you $1. And when we usually do this, I stand out in the hallway, and if the plane doesn't go 10 feet, that means it's a crash landing. Your design was terrible, and your implementation was terrible, and your plane is confiscated and crushed up, and you have to buy new materials. So that adds to your cost, and you have to go back and get another test flight. So that would be your challenge. Can you build a plane with these designs, meeting these requirements, and look at how far it goes and how much money you spent based on these economics? And here are the basic designs, the different designs. The basic design is very simple. The basic dart, which actually flies pretty well, that's why it's cost so much, but it's more expensive for the design to use this design, is a simple traditional airplane. This is a little more fancy. You could have some luck with this. I haven't had a whole lot. Some people have a lot of luck with this one if you fold it carefully. And the hunting. Now, a funny story, years ago I worked for a company, Honeywell in Minneapolis. And on Friday they would have fun things for the engineers to do. And they had a paper airplane contest. And this contest was not for distance, it was for hang time. Who could make the glider start from the 3rd floor of the atrium? We had a big open area at the entrance. The 3rd floor, release your airplane, and who had the longest time. So ideally you would design an airplane to float around in a circle. So it would just gradually lose altitude and eventually hit the ground. So the engineers spent hours that day making their paper airplanes, testing their paper airplanes. When it came time for competition, the guy that won just took a flat sheet of paper and threw it out into the atrium, and it floated one way, and it floated one way, and it had the perfect hang time. It just kept floating and fluttering and fluttering and fluttering, and it won by a factor of 2 or 3. So it was the best for that purpose. In this case, you can't freeform design. You're stuck with one of these 4 designs. But I thought that was an interesting story, that sometimes creative designs win out that you wouldn't even think about. So you have to be careful when you specify your requirements for design. Like it has to go 10 feet. It has to use one of these designs. So that's why engineers typically have requirements on the design. And you have to think about the economics. What impact is this going to have? If I spend 20 tests, is it going to get me a better test, or should I just do 2 or 3 tests? So that's something to think about. And that's it for this section of Virtual Summer Camp. You're going to see College of Engineering and Computing.